to be on the other page. So on Tuesday, we saw the definition of the chain rule. And we have really two ways of expressing the chain rule through this definition, or through two different definitions to express the chain rule. So this is the one we were using most on Tuesday. And so I'm going to try to use this more as we go through the next problem, since it sounds like using this is helpful. However, we'll see that when we use the chain rule in kind of a weird way in section 3.6, this other definition might be more useful. So I'll bring that back up at that time. But both of these were in class on Tuesday, so neither of these are new. But so just as a reminder, our chain rule is that if we have a composite function that has an exterior and interior, to take the derivative of that, we have to do the derivative of the exterior and multiply by the derivative of the interior, being careful that that exterior function keeps that interior in it when we do its derivative. So we did a lot of power rule stuff on Tuesday, practicing this. And we started off getting into exponentials and logarithmics as well. So I want to start off with another exponential. And actually, I'm going to just copy and paste that definition here so it's handy. Okay. So let's start by identifying our exterior and interior functions. So what is the exterior function here if we're starting with f of x equals e to the 6x?
E to the 6x.
Yes, exactly. And so if we are writing it in a way where we're sort of separating these exterior and interior, we can write it as e to the x, which is how some people were preferring to write it. However, if we're just looking at the function, that whole e to the 6x, that whole thing is the exterior. And what is the interior function here?
6x.
Right, exactly. That exponent itself is the interior. So when we have an exponential function, that whole thing is the exterior, the e raised to a power, whereas the power itself will be our interior. So if you are wanting to follow the definition.
Quick question. So that 6x is not the whole power, it's just the 6 with the x, is that correct? Because the x in the exterior is e to the x? Is that?
No, so that this is a reason why I don't, this definition of chain rule is kind of tricky. So if our exterior function e to the x, if we put, so let me rewrite one thing.
I should just take this out of the book.
So remember that this is the exterior. This whole function itself is a composition. So the exterior function is the whole e to the 6x.
Okay.
And so the interior is that 6x. It's the thing that's being plugged into the exterior function.
Okay. Okay. All right. I see it.
Yeah, I think that's a better way to write it on the whole rather than 3x or EX. Seems like it's clearer, you know?
Yes, I agree. But the feedback I was getting on Tuesday was that it was helpful to write it that way. So I'm trying to adapt.
Sure.
But yeah, I agree that it is confusing to write it in this way. Maybe I'll try to just write it in that way. So the I is the thing that's going on the inside. So we have this composition where we have our inside function and then the stuff that's on the outside. So that 6x is the whole thing that's being plugged in. So that's our interior. So if we take, maybe it'll be helpful to write it just this way. If we want to take the derivative of the exterior function, that'll be the derivative of e to the 6x. What is the derivative of e to any power?
The same thing.
The same thing, exactly. So the derivative of e to the 6x is just e to the 6x. So that's our e prime of 6x thing. Whereas what is the derivative of the interior?
6.
Just 6, exactly. So when we are putting this back into our chain rule formula, so we have the derivative of the exterior part, so the e prime of the interior is, ooh, I don't know how I did that. That was weird. The e prime of the interior
You have a ghost in your computer.
Yeah, it seems like it. Technology problems are going to drive me crazy before the end of this year. Okay, so the e prime of the interior is the first part that goes into our chain rule. So that is the e to the 6x. And then we're multiplying with the derivative of the interior, which is just that 6. So you don't have to go through these things that are written on the right side. We can just go straight to the derivative of the exterior times the derivative of the interior. And it looks nicer to just bring that 6 out in front. So now our derivative is 6e to the 6x. So let's do a little one that's a little bit more complex that has some more stuff going on in that exponent. So it might even be helpful to identify the interior first. It sort of depends. So what are our interior and exterior here?
Is interior 2x to the third plus 5?
Yes, exactly. That whole exponent part.
That's crazy to have a power within a power.
Yep. We can have any number of powers within powers. So then what would be our exterior part?
2e to the x?
Yes, and I'm just going to write that interior function in there. So that's our e of the interior, which is that whole power.
Is that IA? In your next to your e?
Oh, that's an of x. It does look like an a, doesn't it?
Ah, okay.
So that whole 2x cubed plus 5 is the I of x, is the interior part. So for I prime, we just need to take the derivative of 2x to the third plus 5, which hopefully the power rule is starting to become more and more natural. So we're taking that 3 and multiplying it with a 2 and then lowering the power by 1. E.
Wait, how did you get 6x squared?
By
Oh.
take.
I see. Never mind.
Okay.
You were frozen for a minute and then I went.
Oh, sorry.
No worries.
So when we do the derivative of the exterior, we're just looking at the sort of basic structure of our exterior function. So it's 2 times e to some power.
6x squared.
So now we're only doing the derivative of the exterior. So up here,
Isn't it the same?
yes, exactly. It's the same.
So the derivative
it's really easy to
will always be the same as the exterior.
For the derivative of the exterior for an exponential, so this is specifically for e to a power, will be the same as it was before. Because
a rule.
Yes, because of our rule. The derivative of e to the x is e to the x, or e to whatever. So that's why on these specifically, the derivative of the exterior is staying the same as the original exterior function. So then when we put this back together, we have our derivative of the exterior, which was just the 2e to the 2x cubed plus 5. It's the exact same since this is an exponential with base e, times the derivative of the interior.
So I got 12x squared e squared times x to the third plus 5.
Yes, so you're just taking that 6x squared and multiplying it in front. Right, yes. And that will be happening next. I just wanted to pause for a second. But yeah, that's right.
Good job, Corey.
Thank you.
So we have the derivative of the exterior first, and then it's being multiplied with the derivative of the interior. So if you don't want to go through all of the I prime, E prime things, we can just go straight to derivative of the exterior part times the derivative of the interior part. Which, once you get more used to the chain rule, really should be what we're just doing, because the chain rule it's kind of like the power rule, which when you do it a lot, it becomes something that we don't have to take so much setup for. It becomes a little bit more natural. It takes a little longer than the power rule does, I think. And yes, exactly. In general, it's kind of weird to leave that 6x squared out in the end. So we would multiply the 6 and the 2 together, that x squared in front. And that's our derivative. A lot of people have the most trouble on the E stuff with the chain rule, just because it is super weird that it doesn't actually change at all between the original function and the exponential function. So we used the power rule a lot last time. We were doing exponentials, and we also know that we use logs a lot. So here's our next chain rule. So we're trying to find g prime if g of x equals the natural log of all of this, x squared minus 4x plus 2. So what is the exterior part here?
Is it just the natural log of 1 over x?
So 1 over x comes when we do the actual derivative. So the exterior part is just the natural log of all of this stuff on the inside of it.
So it's the same thing?
Yes. So we haven't taken the derivative yet. We're just looking at the exterior with the interior on the inside of it. So our interior is x squared minus 4x plus 2.
So why are we doing the E with the exterior with the interior inside instead of doing just E of x?
Because a little while ago, people said that that was more confusing.
Sorry, let me just make it a little more confusing.
Okay. I think that it's hard to just do e of x because that looks like the x in that case is a different x than the x in our actual function. So,
Okay.
Yeah, I'm inclined to agree. It seems like E is by itself just kind of E, and we're not really used to doing things that aren't E yet, so that's okay.
so this, what I just wrote is
Yeah, I
just,
kind of like
what I just wrote is exactly the same as how I was doing it right in B. And how it worked in A. Another way we could write it.
ln to the or ln of I of x.
That, yes, that sounds like a good way to write it. Let's try that. So if instead of writing all of that,
To I of x of natural log.
right, exactly.
That makes sense. Thank you, Lucas.
And then the x throughout the entire process.
Yes, I think that is a good suggestion. Thank you. So our whole function, our definition, let me scroll up again. Our original function, whatever it's called, is the e of I of x. It's this composition. So e of I of x is that whole thing, the natural log of all of this. But then we can separate. I is that inside part, x squared minus 4x plus 2. And I of x is now just being plugged into the natural log, which is our exterior function. So if our exterior is natural log of I of x, what is the derivative of the exterior?
So,
The same thing.
well,
So in this case, we don't have an e. So it's only the same if we have e to the something.
so it's going to be
1 over x.
Yeah.
1 over x,
Yeah.
yes, exactly. So you both said the same thing. So we'll have 1 over I of x. So the derivative of natural log is 1 over x. So here our inside of the natural log is I of x. So the derivative of the natural log is 1 over that thing.
Two x minus 4.
2x minus 4, exactly. So we have the derivative of our function g, our original function, is the derivative of the exterior, e prime of I of x, which is 1 over But now we have to plug I of x back into that thing. So I of x is all of that. So that's our derivative of the exterior. And then we're multiplying with I prime, which is what we just found, 2x plus 4, or minus 4, excuse me. So far, this is our chain rule, all of our parts together, derivative of the exterior times the derivative of the interior. But once we have those parts, we should simplify them. So that 2x minus 4 needs to go up in the numerator. And that denominator stays where it is. We're going to do another natural log, I think, yeah. Any questions about this one? Or any other comment?
Real quick, I don't know why I did it, but I may do it in the future. I put 2x over x squared minus 4x plus 2, and then off to the side I put the minus 4. I don't know why, but it seems right too. I just wasn't sure if that was acceptable.
It's not the same thing, because this whole I prime, the interior, derivative of the interior, is multiplying with the 1 over stuff.
Oh, okay. Yeah.
And so all of that has to go in the numerator.
All right.
Oh, oops. What did I just do?
I think you hit shift and scrolled with your keyboard or your mouse, maybe.
Keyboard, but I don't know. It's fine. We're back. Okay. Let's start with I of x this time. What is our interior?
3x to the 4th plus 1.
Right, exactly. So then we can take that knowledge and rewrite our exterior with that I in it. So the exterior is just going to be the rest of the function, the 2x ln of, and now we have I of x in there.
That definitely feels a lot more comfortable.
Okay, good. So what is our e prime of I of x going to look like?
2 over x or 2 over I of x.
Right, exactly, 2 over I of x. So when we're doing the derivative of natural log, it's 1 over whatever the thing is, but since we have that 2, we can put that 2 up top. And what's I prime?
12x to the, or 12x cubed.
Right, exactly, 12x cubed. So now we can put all of this together. So y prime is going to be e prime of I of x. Putting that I of x back in, so we have 3x to the 4th plus 1 in the denominator. Minus, or excuse me, times I prime, which is 12x cubed. And so for the last little bit, we'll just take that 12x cubed and multiply it with the 2 on top. So all of the chain rule questions that you'll be asked on a test or homework, I think that's true. Let me check for a second. Yeah, okay. We'll have just 2 functions composed like these, an exterior and an interior. And that will be all of that's required. But as we know, compositions of functions can be any number of composed functions. So we could have 3 functions composed, and we would have a chain rule that now has 3 layers to it. We could have 15 functions, and now we would have 15 chain rules. You definitely won't have that. But I am probably going to put an extra credit question on the test that is a 3-layer chain rule, just as an option if you're interested. And so this is an example of what that would look like. And this is kind of where our formula breaks down, which is why I said once we get used to the chain rule, we can't necessarily use the formula all the time. So I'm not going to use the formula for this one, especially since this is an optional concept. So I just want to go through it kind of quickly so you have an idea of what it can look like. So we have this totally outside function, which is the cube that's cubing everything on the inside of it. Then we have this next function, which is the natural log of whatever is inside of that. And then we have everything on the inside. So we do have 3 functions composed here. We have the cube on the outside, then the natural log, and then the 1 plus e to the x on the inside. And so if we're doing the chain rule to find this, we now have 3 layers to go through for our chain rule. So if we're looking at this green part, that's our most exterior function. So something to the 3rd power, we just use our power rule. So we would be or that shouldn't be a 2. We would be bringing our 3 down in front and lowering the power by 2. So that's what our power rule does, right? It just takes the exponent down and lowers the exponent by 1. And everything else in here is staying exactly as it was before. Let me move that in. So then if we have this multi-layer chain rule, we're just sort of working our way inside. So that is the fully most exterior part. Then we would look at this natural log. And we know the derivative of a natural log is 1 over whatever's inside of that natural log. So we have the 1 plus e to the x in there. So that's our next layer of chain rule. And then finally, we have the very interior function. And we would take the derivative of that. So 1 plus e to the x. The derivative of that is just e to the x. So when we're doing the chain rule with lots of layers, trying to set up all of the exterior and interior and functions and plugging them into the formula is not really useful. So we can just sort of work from the outside in and say, okay, our outside function is this just cube. So we use the power rule to take the derivative of that. And everything on the inside stays exactly the same. Then we have our next layer, which is the natural log. Now, derivative of a natural log is 1 over whatever is inside of it. So we have 1 over e to the x. And then we have our little inside layer, 1 plus e to the x, and the derivative of that is just e to the x. So we could do this process with any number of functions that are composed with each other. So this kind of thing will be an extra credit problem on the test, which is totally optional. So if you just want to super focus on just chain rule with 2 layers, that's totally fine. But this is something to know that is possible. And if you ever decide to do the regular calc series rather than business calculus, you will definitely be doing this kind of thing. Okay, let me make sure. Sometimes my chat box just sort of disappears. There it is, okay. So I posted on Tuesday the first part of the homework about product rule, quotient rule, and chain rule. And after today, I'll post more based on what we're doing in 3.6 as well. Before we get started on section 3.6, are there any questions, lingering questions about the chain rule? It does take practice.
So with the natural logs, if there was an exponent that was like, say, a fraction, like 2/3, how would you go about that? So say you have this exact equation that's on the screen, the natural log. So if you take out the brackets and just raise, so if you have natural log parentheses 1 plus e to the x parentheses raised to the third, or raised to the 3 seconds, how would you do that?
So that, what you're describing is a little different from, this will be F.
Right, just like that, yeah.
So the difference between how this one is written and how this one is written are those brackets. So the brackets around this one are saying this entire natural log is being raised to the third power, whereas down here x is being raised to the 2/3 power.
Okay, so it's just that second portion being raised in that case then, right?
Right, exactly.
Okay, that makes sense. Thank you.
You're welcome. And so, just since we have it here, this was something that came up on your last homework 5, the power rule of exponent, or power rule of logarithms. And so this, we would first just bring that 2/3 down. And so it's no longer an exponent.
Gotcha. Okay, I knew I was missing something there. Okay, thank you.
You're welcome. Yeah, so this property of logs. I'll just write it in an ln, but this is true for any log. If there's a power on the thing inside the natural log, it can just come down in front. And now it's no longer as complex looking.
And you don't have to, oh, it's not the power rule. It's the logarithm rule. Okay.
Right, exactly.
Okay.
Yeah, it is usually called the power rule of logs, but I just realized that that's not helpful to call it that in this context. So yeah, it is just a property of logarithms and not derivatives. So in each chapter, there's kind of like some calculus stuff and then application stuff at the end. And so we are going to go into application stuff that is sort of a weird way to use the chain rule. But before we get to the chain rule, I'm just going to put up some information. So section 3.6 is called related rates. So far in this class, cost, revenue, and profit, C of x, R of x, and P of x, have all depended only on production, which is x. And so derivatives give us the rate of change relative to x. So for example, when we are finding marginal cost, we find the derivative of cost, which tells us the change in cost per unit that we are producing, which is great and helpful. But as with anything, there are a lot of things that change at the same time in all of these contexts. And so we have to sort of consider the possibility that X is also changing. Not just as like going up one step at a time when we're thinking about change in cost per unit, but maybe X is its own function of time. So my question is, or the just sort of rhetorical question, what if X depends on time? So if X, our production, is changing with time, then cost, revenue, and profit will also depend on time. So we need to be able to find the rate of change of these relative to time. So if X, which is our production, is a function of time, that means it is X of t. It's its own function. which means that cost and revenue and profit are now composite functions. Cost is depending on the number of units produced, which depends on time. So now cost also depends on time. So we're going to be looking at cost, revenue, and profit as composite functions now, where they depend on time in the end. So this is conceptually what we're doing. And we're going to start with a couple examples of how we can look at the rate of change of these things relative to time. So in order to do related rates problems, which we'll see what specifically that means in a little bit, the derivatives of functions relative to an additional variable, usually time. Here is our question. The previous page, maybe? So our question, or example, so we're going to assume production is changing with respect to time t. So production is x. That's the number of units that we are producing. So we have, if the cost equation is this, we want to change or find the equation for the change in cost with respect to time. So at the beginning of derivatives and throughout doing derivatives, we've seen a few different notations for derivative, and this is where prime notation is not going to work, because we are having to specify exactly what we are taking the derivative, what variable we're taking the derivative with respect to. So the change in cost with respect to time in calculus notation is going to be dc dt. If we just write c prime, that means marginal cost, which is the derivative with respect to x. But we don't want that anymore. We're taking the derivative with respect to time, the change in cost with respect to time. The thing is, there is no t in our equation. So taking the derivative of cost with respect to time maybe feels a little impossible at the moment because there's no t in our equation. However, we have to remember that now production is a function of time. So if production changes with respect to time, x of t is our production function now. So this little x in here is its own function that has a t implied. Even though the t isn't written in there, we're being told in this problem that production is changing with respect to time, which means that x is its own function relative to time. So this means maybe you're selling more fleece blankets in November than you are in June. And so the amount of production that we are doing for whatever it is changing depending on the time. So we have to take this into account when we're looking at cost and revenue and profit. So cost is a composite function. Cost is a function of x, which is also a function of t. So when we take the derivative of cost with respect to time, this is actually a sort of secret chain rule situation. So let's see what this means. So we first would look at cost just like normal. So 5,000 plus 2x is our exterior function. So we would just take the derivative of 5,000 plus 2x like normal first. So what is the derivative of 5,000 plus 2x?
2.
2, exactly. Yes. So we have just 2. But x itself is a function of time. So since we're doing the derivative of cost with respect to time, we have to multiply by the derivative of our interior function, which is x itself. So our exterior is 5,000 plus 2x. Our interior is x, which is really x of t. So our derivative of our interior in this case is dx dt. Because we are taking the derivative of x with respect to time. The thing we don't know here is what the actual function x of t is. We don't know how x is changing with time right now. We just know that it is changing with time. So our dAc dt equation ends up having dx dt in it because the change in cost depends on what the change in x is doing. And so I'm going to come back to this in a moment, but I'm going to go backwards for a minute, back to these definitions of chain rule. So I said earlier that this EI definition of chain rule doesn't work as well for 3.6. And so we have this other definition of chain rule, which is really what we are working with here.
Do we need to memorize this one?
And which is why I don't like to get too stuck on either of these. So this is what I was about to say. I don't like getting stuck on either of these definitions of chain rule because they mean exactly the same thing. They're just sort of, this notation is different. That's the only thing that's different. And so you will not be given any definition of the chain rule on the test. And so you need to know how to use the chain rule. So the important part of related rates in this kind of problem is that if we're trying to find the change in cost with respect to time, we're doing the derivative just like we normally do. So we're doing the derivative of 5,000 plus 2x, but then we have to recognize that x is also its own function of time. So then we're just multiplying by a dx dt. And that little dot notation is not necessary since we're just multiplying. So the derivative of cost with respect to time is just the regular derivative of cost multiplied with dx dt. This can look strange at first, but all we're doing is the regular derivative. There's no new derivative rules happening here. We're just taking the derivative of c like normal and then thinking, oh, x also changes with time. So we also multiply by dx dt. Let's do another one. Leave that one up as a reference.
So would it be 4 dx dt?
Yes, exactly.
Okay.
So we're doing now dc dt, which is the derivative of c, which is just 4 times the derivative of x. So these are both cost equations that are just a linear equation where we have a coefficient of x. So now let's look at a revenue equation that's a quadratic. So now instead of finding dc dt, we're finding dr dt. So we need, actually, I'm gonna rewrite the revenue equation so I can make notes on it. So this revenue equation is a sum of things, which the cost were also, but they had a constant in them. So for this revenue equation, we have a 10x minus 0.001x squared. So we have to go through each term here and do the derivative of each term. So if we have 10x, and we want to take the derivative of that with respect to t, what will that end up being?
Ten.
10, so that is the derivative of 10x. And we need a little bit more on there.
Is it dx over dt?
Exactly, yes. So if we were doing the derivative with respect to just x, so we would get just 10 there. But since we're doing the derivative with respect to t, we get 10 with that dx dt to show that the x is also changing. So then we can go to the next term. So what will we get for this next term?
Negative 0.002 dx over dt.
Almost.
X, the
Yes,
dx
there-
over dt.
So you keep the
Yeah.
extra x.
We do, because of that, that is a power rule. So we're multiplying the 2 down, which we have. And then the x is still there because its power was lowered by 1. So this part, if we ignored those dx dt's, everything else should look exactly the same as if we were taking just a regular derivative. The only thing that's different is that we have to put dx dt on every time we have a term that has an x in it.
So far we've done a cost equation, a revenue equation, and what was the first one? A cost equation also?
Yes, those first 2
Okay.
are both costs.
Okay. Thank you.
Real quick, Mandel. So the way I'm understanding it, anyways, is every time we see the equation, well, I guess like for C is R equals 10x minus 0.001x squared. When we're looking at that, we're actually seeing 10x times t because of the time part, right? Because of the x
10x of
of
t.
t, right? Okay, yeah, all right. And then when we take the derivative of x of t, that's the dx over dt, and then at the end we're just kind of multiplying that by the derivative of r equals 10x minus 0.001x squared.
Yes, exactly.
Okay.
So these the x's in the revenue cost profit equations will never have a t with them, but that's absolutely right. All of these x's in here are functions of t. So we could write it, we could see it as, if we think of this as r of x of t, oops. This is 10x of t minus 0.001 x of t squared, which is never going to be how it's
Yep,
written.
that's exactly what I.
Yeah, we won't see that in any equation. And And it's a little messy to write it this way, but that is what's happening. It's like that of t part is just implied in there. And so that is like our interior function. So when we do the derivative of 10x, we get the 10, but then we have to multiply by the derivative of x of t, which is dx of dt.
So will the derivative of x to the, or xt, will that always be dx over dt? Always, right?
Yes, exactly. And that's why this is the chain rule in action, but it's different because we're never going to know what the function x actually is. So our derivative of x will always just be dx dt. So this is why this section is titled related rates, because once we have this equation that we're looking at for the dr dt, this equation is relating the rate of change of r and the rate of change of x. And so it's relating these two ways that the variables change with each other, which is a really important part of calculus. Calculus is all about how things change together. And so now we're seeing that we have this equation that it still has an x in it, but everything else, all of the rest of our like variables are rates of change. So we're looking at how things change together. And I also want to make a little note as well about notation. dr dt, dx dt, these things are whole parts. So dx dt is like its own variable. dx dt is a whole thing together, and that's the rate of change of x. Sometimes people really want to see that as dx and dt separately, which sometimes it is in calculus, but not right now. It's one thing. It's the rate of change of x with respect to time. So when we are using these equations, so we're about to look at an example where we actually put all this stuff together. When we're using these equations, dx dt is a whole part. That's like its own variable piece. dr dt is its own part, and x is its own part. So let's look at an example of how we can use these to actually find some information. And let's see. So I'm going to give you a bit to read through this problem and take your notes. And I can't fit it all on here, but these just say cost, revenue, profit. But we're going to start with cost anyway, so I'll just leave that one only up on the screen. Okay, so let's start to look at this. So a company manufacturing calculators, the cost, revenue, and profit equations are given by these three things. So as long as we know cost and revenue, profit is always just revenue minus cost. And production output in 1 week is X calculator. So we're producing X calculators per week. So we're also given this information. Production is increasing at a rate of 400 calculators per week. So we're making more and more calculators every week. At the time that we have an output of 4,500 calculators. We want to find the rate of increase or decrease in cost, revenue, and profit. So starting with cost, I'm just going to rewrite that equation, 80,000 plus 20x. Oops. So if we are trying to find the rate of increase or decrease in cost, we need to know the equation for the change in cost with respect to time. So that's the first thing we should find, dc dt. 20
dc dt.
Almost. We will have a
Dx,
dt.
sorry, dx dt.
Yes, exactly, dx dt. So we're looking at the change in cost with respect to time now. So we take the derivative of cost, which is just the 20, and then we have that dx dt on there as well to show that it's changing with time also. So I'm going to put up a poll question in just a moment, asking about this information we know. So it's not asking just for the equation for dc dt. We want to know when production is increasing at this much and output is this much, what is the increase or decrease in cost? So my question is about what those two numbers, 400 and 4,500, represent. So I just launched a poll for a multiple choice of what are these numbers 400 and 4,500 telling us we know. So a little bit longer on that poll, and then we will talk about it. So if you haven't answered the poll question, you have 10 seconds. All right. Awesome. So we are kind of Lots of votes for all of them, but the winner pulled ahead with just 53%. And that is the correct answer before I reveal that. This question is saying production is increasing and production output. What variable represents production?
X.
X, exactly, yes. So our production is X. So I threw in P as one of those options just to try to be tricky. It didn't really work. So production is increasing at 400 calculators a week, and production output is 4,500 calculators. Those are the two numbers we have. This statement that production is increasing means that we have a rate of change. Anytime we see increasing or decreasing, that implies there's a rate of change going on. So production is the thing that's changing. So that would be dx. And it's increasing per week, which means it's changing relative to time. So that would be a dx dt. So dx dt is our 400 calculators per week, because that's how production is changing relative to time. Just x would be the 4,500, since that's how many we're currently producing. So we have these two given numbers in our problem, the 400 and the 4,500. And so each of those is a part of what could be in our dc/dt equation. We don't have an x in our dc/dt equation, but we do have dx dt. So this is what I was saying on the previous page, that whole dx dt together is its own variable. So we can replace that dx dt with 400 for our particular problem. So now we have that the rate of change of cost is going to be 20 times 400.
8,000.
Yes. And what are our units on that 8,000?
Is it dollars?
Dollars is part of it.
Calculators?
Per week.
Per week, exactly.
Dollars per calculator.
Per week. So that's the difference between dc/dt and c prime. Now we're finding the rate of change over time rather than in per calculator, like we do for our marginal cost. So here cost is changing at $8,000 per week. So that's cost. We were able to find the dc/dt equation, which tells us how cost is changing relative to time. Once we have that, we can plug in the information we know to find the change in cost per week at those specific given values. So we can do the same thing for revenue. Oh, sorry, go ahead.
That's an increase per week, correct?
Yes, exactly. Since it came out to be positive, it is increasing. So I'm going to rewrite our revenue equation down here. 250x minus x squared over 20. So task number 1 is to find dr dt. So take a moment to try to do that before we put it together.
Is it negative x over 10? dr dt?
That is part of it. So that would be what we get on this term, dx dt.
So before that's the 250, right? So 250 minus x over 10 times dx dt.
Yes, and we need the dx dt on both of them because we're doing the derivative of each term. And so every time we do the derivative of something with an x, that dx dt is coming with it. So
I'm confused on the x squared over 20.
So when we do the derivative of x squared over 20, that is a power rule. So the 2 would come down and we would end up with 2x over 20.
Oh, okay. I got 2x over 20, but I was like, how did I come to x over 10? Gotcha. Okay, that makes sense now.
Okay.
Oversight.
Does each factor that has an x get a dr dt no matter, or dx over dt no matter what the power is?
Yes, exactly. Yes.
So even if it was a 5, it would still get a 1 dx dt?
Correct, yeah. Because the power only affects that exterior part. So we're doing the derivative of that with the power rule, but then we're looking at just the x as the inside and taking the derivative of that. So that's the dx dt.
So for instance, if that was 1 over 20, then that wouldn't do anything, right? It'd just disappear because of the
Right.
power rule? Okay.
You mean a 1 over 20, like just a 1 over 20?
Yep. Yeah.
Yes. Yeah, that
Okay.
would go away since there's no x in it. So we would not have a dx dt in that case because it's just a constant. And that's what happened up here, that 80,000 just is gone.
Thank you.
Mm-hmm. So once we have our dr dt equation, now we're looking for the change in revenue with respect to time. And we still have those same 2 pieces of information. So our dx dt was the 400 and x was that production level of 4,500. Yeah.
Go ahead. I finished. I just wanted to see if my answer was right.
Oh, well, I don't know what it is yet, so we have to plug them in and find out anyway. So we took our 400 and 500 from the information from the problem, the change in production and the production itself, which are dx dt and x. And so we can just plug those right into our equation. So now our change in revenue with respect to time. We have 250 times that 400, the dx dt, minus 4,500 over 10, for the x over 10, times 400. So we're just putting in those two given pieces of information about the change in production and the production itself to our dRdt equation. And all we have to do now is evaluate. I got negative 80,000. Did anyone get anything different?
Nope.
Okay, great. Always wary of calculator input issues. So in this case, we do have a negative instead of a positive. So for the cost, we are increasing $8,000 per week since that was a positive result, but now we have a negative, which does mean revenue is decreasing. By $80,000 per week. So the last part of this question was profit. Profit, we don't have to work very hard to find. Once we do all of the work for revenue and cost, profit is nice. So profit is always equal to revenue minus the cost. So the money we're bringing in minus the cost, or the money we have to spend to produce stuff. So if we want to find the change in profit with respect to time, because of derivative rules, when we take a derivative of something, we can take the derivative of each part separately, each term. Any derivative of profit is just the derivative of revenue minus the derivative of cost. And that's true whether we're doing these derivatives with respect to time or with respect to x or whatever. So another little note is that if we're doing marginal profit, and you did some homework on this a while ago, that's also equal to marginal revenue minus marginal cost. So it's always true that if we're doing a derivative of profit, it's the same as just the derivative of revenue minus the derivative of cost. And this is extra nice because we have the same situation throughout all of these. We're looking at the situation of a change in production of 400 units per week at a production level of 4,500 units per week, or excuse me, 4,500 units. So we've already found DRDT and DCDT for each of those things. So to find profit, we don't even need the actual equation. We can just plug in our answers from part B and part C. So profit is really nice. As long as we've done revenue and costs already, we just subtract them. And so our cost is increasing and our revenue is decreasing. So it shouldn't be a surprise that profit is also decreasing since we're spending more but making less.
They need to get out of the calculator game. They're not making money.
Yeah. So profit is decreasing to $88,000 per week. Yikes.
This one was lots of fun to do, by the way.
It's nice to see all these calculus things coming together.
Yeah, it's cool.
Any questions or comments about this problem? So I want to take a moment to stop and talk about what's coming up, because believe it or not, test 2 is on the way.
That was quick.
I know, but it's about 3 weeks in between, which if we have 16-week term, 4 tests and a final, that's about right. So looking ahead, I have copy and pasted part of the syllabus because I want to take a vote on when to have the test. After the adjustments for that snow day that wasn't really a snow day. Test 2 landed on March 2nd, which is a Tuesday. But so today is 3.6 day, and we did that. On Tuesday, next Tuesday, we will cover section 3.7, which is the end of chapter 3. So my plan, and this is, I said maybe Thursday 2:25, but I think we can finish 3.7 on Tuesday. But if it spills over to Thursday, that's possible. And so on the homework 7 will be about section 3.7, and it'll be due on the 2nd. So I thought maybe this would be undesirable to have the homework due the same day as the test, since maybe you wouldn't have finished it or gotten feedback. Sorry, there was a comment.
Yeah, no, I think that's a lot.
Okay, so the other option would be to move the test to March 4th. The thing is, if we do that, then 4.2 is good, would be moved to March 2nd. So I think there are pros and cons of both of these because we are going to be starting chapter 4 on next Thursday, which will not be a part of the test. So our two options are these. Have test 2 on Tuesday the 2nd as scheduled. And the con, I think, is that the section 3.7 homework is due the same day as the test. Option 2 would be to have the test on Thursday the 4th, and the con is that we would have 2 classes of chapter 4 before the chapter 3 test, which sometimes I hear. So I am going to
Does
put up
chapter
a
4
poll.
have like, oh, well, quick question. Does chapter 4 have like the power rule was to the other tests that we took?
I'm not sure what you mean. I'm sorry.
No, that's fine. So like when we did the 4-step process as opposed to doing the power rule, how we basically just, is there in chapter to make it easier to do stuff that we're learning in chapter 3?
No, there's not.
Okay.
Yeah. Chapter 4 actually uses the stuff that we have been doing, but it's all about graphing. So it'll,
Okay.
there's nothing that'll make chapter 3 stuff easier.
Would it be a possibility to push back the due date to Wednesday if we did the test on Tuesday?
I could do that. I guess my sort of concern
Yeah, I
is
think that would work the best.
So, okay, so I just want to clarify, then you would be doing the section 3.7 homework. The section 3.7 homework would be due after the test then. And
I see.
that is
Okay.
on the test.
I gotcha.
So I have a poll to take votes on these two options. One of the options is no preference. So option 1 is have the test on Tuesday the 2nd. Option 2 is to have the test on Thursday the 4th. And the other option is no preference. So are there any other questions or comments before we have a vote? Okay, I am going to launch the poll. Oh, it's close. So while the last couple people are deciding, I'm just going to bring up our Canvas page because regardless of what day the test is on, I have posted a little bit of information about the test. So in the week 8 module, so right now, the Tuesday 3-2 test today, but it might change. The internet is freezing. So I put up an information guide like I did last time and a practice test. So both of those things are up now in that section. So if you want to start looking at those, they are available. Okay, and the polling has come in. I'll share the results. So the majority have voted to have the test on Thursday the 4th, which is 2 weeks from today. And 12% said no preference. So I think that having it on the 4th sounds good to me. And I will make an effort to get that homework graded before the test as soon as I can. So I will move these things to that day, to the Thursday the 4th, but there is some information about the test up now for you to view. And I'll post the rest of this week's homework now. And that is all for today. So have a good weekend.
Thank you.
Thank you. Have a good day.
You too.
Bye-bye.
Bye.
So I just had a thing come up for next week. I have a doctor's appointment on Thursday, so I may or may not be able to make